Okay, so this video is about the thermal physics part from module 5. So just some guidance. So to use this video effectively, you should have already gone through and learned the physics course at this point, because this is a revision tool. And the second thing is, in the description to this video, I've put a link to the document that you can be filling in, that you can see a screenshot of on the right-hand side, so you can use that. And what you should be doing is, before I go through each section, you should pause the video and work through each section at a time. And then finally, the last thing to say is this is not a task you should do once. So the reason I've given you a template is you can do it as many times as you like to see how well your understanding and knowledge is developing. The second thing is, alongside this video, I've created a memorized course for practicing the key terminology from the thermal physics part of the course. And again, a link to that is in the description. Okay, so let's get cracking, looking at module 5 and starting with 5.1.1, which is about temperature. So the first thing I'd like you to do is pause the video now and work your way through this section. Do as much as you possibly can. Okay, so I'm going to assume you've worked through 5.1.1. So let's go through each of these. So thermal equilibrium is when the rate at which two objects exchange thermal energy is 0. So essentially each of them is transferring the same energy either way. And that means that they are at the same temperature, or the temperature difference is 0, whichever way you like. So we have two main scales of temperature that we use. There is another one, Fahrenheit, which the Americans use for some unknown reason, but we use the Celsius scale and the Kelvin scale. So the Celsius scale was one that we just invented. I think he's Swedish, Celsius, the guy who invented it. So it uses two fixed points. It uses the melting point of ice and the boiling point of water as the fixed points. So every thermometer is calibrated to these temperatures, and then the difference is just divided into 100 sections, which we call degrees. Kelvin is different. We don't base it on any physical property. We just say that absolute 0 is at 0 Kelvin and go from there. So it's not based on any material. But it's useful to be able to convert between the two, because Celsius is very commonly used in and around us. In physics and other science, we use Kelvin. So to convert between them, we just add 273 to Celsius to get Kelvin. And in this topic, pretty much all the temperatures need to be in Kelvin in equations, so it's something to think about all the time. Okay, so moving on to the second section. Again, we've got a fair amount in this section looking at the different states of matter. So these are what the specification says we should be able to do. So again, work your way through this section and then we'll take a look. Okay, so let's look at each of our states of matter in terms of spacing first of all. So you should know that solids, the atoms are very closely packed together, and in liquids they're pretty closely packed together as well, not quite as close, whereas in a gas they're very far apart or have big spacing. In a solid, there is a really regular arrangement to the atoms, whereas in liquid and gases the atoms are just arranged randomly because they're free to move. In a solid, they are in very slow and they're locked in fixed position, so they can only vibrate. Whereas in a liquid, they are still fairly slow, but they are free to move past each other, which is why they're arranged randomly. And in a gas, they're fast moving, but again, free to move. Okay, so the next one, describe the simple kinetic model of matter. So this is the way of modeling a solid, a liquid, or gas by considering the kinetic energy of the individual atoms and their collisions. And as we'll see, we also start to think about their electric potential energy as well. But this is what essentially we mean by the kinetic model. And there's an experiment you can do to actually evidence that this is the case, that things are made of these small atoms with kinetic energy that we can model. And the experiment is called the Brownian motion experiment. So what you do is you inject smoke particles or dust, something, into a container of gas, and you look at it under a microscope. So you're not going to see it with the naked eye, but you will see it under a microscope. And what you observe is that the smoke particles are not colliding with each other, and yet they keep randomly changing direction. Which would appear to disobey Newton's laws of motion, unless there's something invisible that we can't see colliding with them that's much smaller. And this is our evidence that there are these gas atoms. Okay, so when we're looking at changing states of matter, we're going to be talking a lot about internal energy. And internal energy is the sum of a system's kinetic and potential energies. It's kind of all of the energies lumped together to give one value. So we've talked about absolute zero a little bit already. So absolute zero is related to internal energy because it's the temperature at which a system has minimum internal energy. So you can never take away all of the energy exactly. The atoms are always slightly vibrating. Otherwise, you'd violate Heisenberg's uncertainty principle, but you can reach a minimum at absolute zero. And there's quite a nice relationship between internal energy and temperature, especially with gases. But as a general rule of thumb, if you increase the temperature of a material, you're going to increase its kinetic energy, and so you're going to increase its internal energy. But it doesn't necessarily work the same way. You can increase the internal energy without increasing the temperature. So it works one way, but not the other. And the reason for that is during a phase change, you can essentially transfer thermal energy to electric potential energy or the other way around. And that would mean the internal energy would change, but the temperature stays the same as we haven't changed the kinetic energy. Whereas when the temperature changes, thermal energy is transferred to or from kinetic energy and electric potential energy. And we usually ignore the electric potential energy change mostly, but we do know materials expand or contract. Okay, so moving on to part 3. Again, we're now looking at mathematically modeling those changes that we just looked at. So again, work your way through this section, looking at the different properties and the experiments. All right, so now you've had a chance to work through it. Specific heat capacity, the thermal energy required to change the temperature of 1 kilogram of substance by 1 degree. And it doesn't matter if those degrees are Kelvin or Celsius, it's the same. So what that's essentially saying is specific heat capacity is Q, which is a symbol for thermal energy, divided by m delta T. And we can do an experiment to find out the values for materials, which we can then use in our calculations. So this is an electronic method, so what we do is we connect a heater into a circuit, and we're going to need an ammeter and a voltmeter to measure current and potential difference. And we're also going to need to measure the mass of the object. You can see in the equation we're clearly going to need the mass. And the thing we need to make sure is that any thermal energy we're supplying is going to the material, so we're going to insulate the material to stop it exchanging energy with the surroundings, or at least minimize that. Okay, so what we're going to do is tweak the equation slightly. So Q equals mc delta T. Energy would be power times time. So we can put that in place of Q. And in place of temperature difference, we can put the final temperature minus the initial. And in terms of power, we can put VI. And then we can rearrange it to make the final temperature the subject of the equation. So what we're going to do now is we're going to turn on the heater and record the potential difference, current, and measure the temperature every 30 seconds. So what we can do is plot a graph of temperature against time, because temperature on the y-axis, time on the x-axis, and we can see that the gradient would be equal to VI over MC. We want C, so we're going to need VI divided by M times the gradient of the graph. Okay, so moving on to look at phase change. So specific latent heat of fusion is the property we use to deal with converting from a solid to a liquid, and it specifically is the thermal energy to change 1 kilogram between them. For vaporization, it's the same idea, the energy to change 1 kilogram, but this time between a liquid and a gas. And the equation looks something like this. So there's no temperature in there because temperature does not change during a phase change. And again, the experiment to do this is very, very similar. We're going to use the same circuit, but we're going to use this new equation, but again, we're going to substitute in VIT for Q. So again, we're going to need the mass, as we can see from the equation, and we're going to need the potential difference in current readings. And this time, although we're not going to use it in the calculation, we're still going to record the temperature every 30 seconds until the material has completely changed state and the temperature starts to rise. So what we're going to do is calculate the time which the material was at constant temperature. So initially it might have increased, and then at the end it might have increased. We need the time it's at constant temperature, and so it was changing phase. Then we can plug in VIT and M into the equation to get specific latent heat of fusion or vaporization, depending on which state you were looking at. Okay. So moving on to look at gases, these are the things that we need to be able to do with our gases. So there's quite a few different things that we'll take a look at. Okay. So again, work your way through the section, then we will take a look. Okay, so first off, Avogadro's constant. This tells you the number of molecules of substance in 1 mole, and it's the same for every single substance there is, 6.02 times 10 to the 23. So we can see that 1 mole contains a heck of a lot of atoms or molecules. So what we're going to do is to look to model gases by considering them as particles with kinetic energy that are colliding. So in order to model this, we do have to make some assumptions. Most people consider that to be a bad thing, but it's not, because these assumptions are all incredibly valid, but they help us get a nice simple model. So the first assumption we make is the mass of a molecule is negligible compared to the container, well, the mass of the container, which makes complete sense if you think about the scale of the atoms. But we need that in order to be able to have elastic collisions, and that in those elastic collisions, the molecule keeps all the kinetic energy. We need that to be the case. We also need the volume of the molecule to be negligible compared to the volume of the container, because that's going to make the collision time, or the time it takes to collide with the wall, negligible compared to the time it takes the particle to go bounce off the other wall and come back. And the final thing we are going to assume, which is incredibly valid, is that the molecules travel in a random way, they obey Newtonian physics, and that the forces between the molecules are negligible. And what that last point means is we don't need to consider electric potential energy anymore. We just think about internal energy as kinetic energy. And all of those things put together give us an equation for pressure. So we're going to start off with Newton's second law, forces equal to the rate of change of momentum. But because the collision time is negligible, the time between collisions is going to take the time it takes for a gas particle to go between collisions. So it's going to go the length of the container and then come back, which is why the distance is 2L. And then we just end up with mv squared over the length of the container. Pressure is force over area, so we're just going to divide that by the area over which the force is spread, so the area of the wall. So this gives us a way of figuring out pressure and the factors that affect pressure in a gas. So what we're going to do is use that to explain a few things. So if you increase the temperature of the gas, you increase the average kinetic energy of the molecules, which means their root mean square speed is going to increase all that, their average speed, if you like. And what that's going to mean is the momentum change during a collision is going to be bigger. So if the cross-sectional area and the length are constant, which it would be if it's constant volume, the increase in the momentum change will cause an increase in the pressure, which is exactly what we'd expect from our other equations. Increasing temperature does increase pressure. If we decrease the volume at constant temperature, well, if the temperature is constant, the momentum change is going to be the same now. It's not going to be any different, but it will decrease the area, the length of the container, and so effectively it's going to make the time between collisions shorter. And both of those things will act to increase the pressure because they're on the bottom line. So if we decrease them, that's going to make the pressure bigger. Okay. So we're going to move on to the other way we model gases using the ideal gas equation. So this equation has a relationship where so P is pressure, V is volume, N is the number of moles of a gas, R is the molecular gas constant, that just has a fixed value 8.31, and temperature in Kelvin. So you can see this equation also predicts that increasing temperature should increase the pressure, or decreasing volume should increase the pressure at constant temperature. So you can see this gives us the same model, it's just a different way of doing it. So Boyle's law is a specific scenario that says at constant temperature, pressure and volume are inversely proportional, which we can see from that equation. So if we want to investigate that, we're going to need a setup that will allow us to vary the pressure and measure the volume at constant temperature. So if we're going to be able to calculate the pressure that we're applying, we're going to need to know what the area we're applying it over is, so I'm going to use a micrometer to measure the diameter of the syringe so I can get the area. And the other thing I'm going to do is I'm going to measure the atmospheric pressure using a barometer or a pressure gauge. So we've got measurements of initial pressure and initial volume because the syringe has volume lines on the side. So what we're going to do is we're going to seal the syringe so we've got a fixed number of moles of gas. And we're going to add masses to the wooden block and record the volumes for the new volume anyway as we add those masses. So what we're going to end up wanting to do is plot a graph of pressure against the reciprocal of volume, and if they're inversely proportional, that graph should be a straight line through the origin. So first we're going to need a way of figuring out what the pressure is inside the container, and the way we're going to do that is so we're going to take the atmospheric pressure, and then as we add masses, we're going to add to that pressure, and we're going to add the weight force of the mass divided by the area over which it's applied. So that will give us the pressure, and then we can plot the graph to see whether Boyle's law works. Okay, so another experiment we can do in this topic is find out or measure the value of absolute zero. So we need slightly different equipment for this one. We're going to need a water bath because that will give us a way of accurately controlling the temperature of the surroundings. And we're going to need a pressure gauge or a barometer and a thermometer too. So what we're going to do is make sure our container of gas is sealed, so we've got a fixed volume and a fixed number of moles. And we're going to connect it to our barometer or our pressure gauge, and that's going to allow us to measure the pressure. So we're going to measure the initial temperature and the initial pressure. That will be our first set of readings. And then what we're going to do is we're going to increase the temperature of our water bath to increase the temperature of the surroundings. And if we wait long enough, the gas will reach thermal equilibrium with that and it'll be at the same temperature. And we're going to record the new temperature and pressure. We'll repeat that step like 5 more times, so we've got a nice set of data, and plot a graph of pressure versus temperature in Celsius. So to modify the equation slightly so we can deal in Celsius, PV equals nRT assumes the temperature is in Kelvin. So we're going to need to subtract the value for essentially the absolute zero from our value of T, so we can convert it into Celsius. Then so when pressure equals zero, what that's going to mean is that the temperature of the system will be equal to absolute zero. So that's what the equation predicts. At absolute zero, we should have zero pressure. And so that's what we would do. We'd extrapolate back our data, so we should get a straight line graph, extrapolate it back, and when it crosses the x-axis, when pressure is zero, that will give you T0 or absolute zero. Okay, so then getting on to modeling gases as a whole, because essentially everything we've looked at so far has been looking at one gas molecule. Now let's scale it up to look at a whole system of gas molecules. So one of the tools we use is something called mean square speed. And what that is the sum of the speed of individual molecules squared, so sum of the squares of molecules divided by the number. So it's literally the average square speed. So this allows us to model a whole system of gases which are all the molecules are traveling at different speeds. And another thing that allows us to model them is something called a Maxwell-Boltzmann distribution, which looks something like this. So this allows us to see the impact of increasing temperature on the root mean squared speed of gases, or the kinetic energy, effectively. So you can see from the graph, increase in temperature increases the average kinetic energy, or the RMS speed, or the root mean square speed. We can also see that increasing the temperature also increases the range of possible. So some of them can start, the maximum kinetic energy, if you like, gets much higher. So we have a much bigger range of possible values there. Okay, so one final way we model gases is using something slightly different called the equation of state, which looks like this: PV equals nKT. And I'd just like to draw your attention to the fact the N is different. This N stands for the number of molecules of your gas. So this equation is fundamentally the same as the ideal gas equation, because the K, the Boltzmann constant, is the molar gas constant divided by Avogadro's number. So if we multiply that by the number of molecules, that turns into the number of moles times by R, because N divided by the Avogadro's number gives you the number of moles. So then you can see that these two equations are identical. They've just got different properties in them. So last thing we're going to do is look at relationship between the average molecular kinetic energy and temperature. So we can see the relationship which the Maxwell-Boltzmann distribution gives us. So from our kinetic model, we got to the point where we worked out what the pressure of the gas is based on one molecule of gas colliding in one direction. So what we've got on the top line here is a slightly modified expression which allows us to figure out the pressure with a whole system of gas particles. So we've got n gas particles, each of mass m, and they're in a container of volume v, and they have a certain root mean square speed. We know that PV equals nKT from the equation of state. So what we can do is we can cancel out the capital N's, or the number of molecules, in the next line. Then what I'm going to do is multiply both sides by 3/2, so the left-hand side becomes the average kinetic energy, and the right-hand side becomes 3/2 kT. And what that means is the average kinetic energy can be calculated by doing 3/2 kT. So if you know the temperature, you know the average kinetic energy, and there's no other factors involved. Internal energy for a gas, remember we ignore intermolecular forces, so we ignore electric potential energy. So it's just going to be the sum of the kinetic energies, which will be the number of molecules times by the average kinetic energy, so 3/2 nKT. So to get the total internal energy, all we need to know is the number of molecules and the temperature. Okay, so that concludes this video looking through the specification on thermal physics. Thank you for taking the time to watch.